So far we've been dealing with we've talked about resist. Oh, I haven't made a video on resistors yet. I'm gonna make a video on resistors, but I'm making this for people who might already have a good understanding of resistors and capacitors. We've dealt with what's the word? Resistors in series, resistors in parallel, capacitors in series, capacitors in parallel. We've dealt with all of that. And knowing the parallel rules and the series rules can help us with circuits like this, right? Kind of basic circuits that you would see, but it wouldn't really help us with circuits like this, right? Because it's like, what the heck? We have like a resistor forming a triangle with another resistor, and then they're coming back to the same thing, right? Just understanding Ohm's law and resistors in series and parallel, all that stuff, is not going to be the most helpful thing in the world to do to solve or understand, like kind of what's the voltage across this one, what's the current across this one, what's the voltage across this one, you know, given all the resistances or whatever. It may not be the most helpful thing in the world. We gotta use Kirchhoff's laws. So Kirchhoff's laws, I'm going to explain both of them. We have the junction rule. I like to call it the current rule, dealing with conservation of charge, and we'll get to that, as well as the voltage rule, which is kind of like a conservation of energy rule. That's also called the loop rule. So let's start with the junction rule. I think the junction rule is the first one. Well, it's the one that's very easy to grasp. Here's really what the junction rule is saying. The junction rule is saying, let's say we have a current passing through this wire, and we'll call it I naught, like kind of the original current or whatever. A junction is when three or more conductors meet at one point. So we have this wire connected to this wire connected to this wire. We call this a junction. This would not be a junction. We only have two. This would not be a junction. We only have two. This would be a junction. So in this example, this would be a junction, right? 1, 2, 3. You know, this would be a junction. 1, 2, 3. I don't think you have to remember. Like, you don't really have to memorize. Wait, is a junction with 3 or more or 4 or more? Because when you actually understand what the junction rule is saying, it'll kind of make sense. Like, when can you use it? Do I use a junction rule here or here? What's a junction? It'll make a lot of sense. When I get to it, all the junction rule is saying is that, hey, some of this current is going to go to here. Some of this current is going to go to here. At the end of the day, the total current that has gone through here and here has to equal the current here. So I naught, right, the original current has to equal I1 plus I2. That's all the current rule is saying, right? And this makes sense. If you have an original amount of current here, then the total has to equal I1 plus I2. And then when this current gets out, it's going to join back up, or I'll say I2, it's going to join back up at this junction, and then the leaving current has to equal I naught. So this I naught did not change in size throughout the whole circuit, that total amount of current. This is just because of the conservation of charge, right? So if we think about, well, this is really just the same as dq total over dt equals dq1 over dt plus dq2 over dt. If for some reason we had more currents, like through I2, right, where I2 plus I1 is greater than I initial, that's suggesting that, hey, dq1, that amount of charge going through that first one, plus the second amount of charge, is somehow greater than the original total amount of charge, which can't be true, right? That breaks conservation of charge. Don't quote me on this, but I think that's also related to conservation of mass, because I think atoms are the thing, like the proton and the neutron, like a proton and electrons. So how can you get more electrons if there's more charge? I don't know. I have to study that a bit more deeper, but definitely breaks the conservation of charge, which is why I initial equals I1 and I initial equals I1 plus I2 plus so the current here is going to equal, right, this current plus this current, and they're going to all connect back up here. So that's really just what the junction rule is saying, right? And this is why, like, you could technically apply the junction rule here, right? I here has to equal I coming out of there, right? There's no way that charge would have gone anywhere else. Like if this was a perfect conductor or something like that. So that's really the junction. Hopefully that makes sense. That should hopefully make sense. And if you have more questions, please feel free to ask. But I think the voltage law is the one that might not always make the most amount of sense. So here's what the voltage law is saying. Let's say we had a battery here, and let's say we have two resistors like so. Okay? What the voltage law is saying, the loop rule I like to call it, and I'll talk about loops as well. What the voltage law is saying that, hey, the sum of all the electric potential differences, all the voltages, has to equal 0, right? Now, let's think about what that is saying, like why that's the case, right? What is it? We know, so let's say we have some current coming through here, right? We know that batteries add potential energy to the charge, right? It's analogous to climbing up like a large amount of stairs. So V1, we'll say this is V1, right? You're gaining potential energy as you go through the battery, right? Then the resistor is going to take some of that energy and convert it to, I don't know, light or heat or some form of energy, right? If the resistor is a light bulb or, I don't know, a heater or something, I don't know. It's going to use some of that energy. So it's going to have a certain amount of voltage going through here. As you get to the resistor, there's going to be a voltage drop, right? Because it has to use some of that energy. So now, will it go back to 0 where it originally started? Well, if you think about it, now this current has to go through here, and there needs to be, in order for this resistor, right, to use its energy, there has to be energy there. So this is not going to completely get rid of V2. Instead, or the original voltage is going to V2. As you go in through the next resistor, it's going to take even more of that energy. Now, by the time you're done with V3, you have to have no voltage left, essentially, right? Because if you still had voltage for whatever reason, you could go through this battery and it'll keep adding energy, right? Imagine you were here, right? You still had some voltage left. Well, this battery is going to add the same amount. And it's going to go through that whole thing again, and it's going to violate the conservation of energy. So what that means is, right, so in order for energy to be conserved, the total sum of voltage has to be equal to 0. So what that means is V1 has to equal the voltage across these two resistors. So I'll say actually not V1, I'll say V initial, right? So what that essentially means is, What that essentially means is, well, we can also replace, by the way, we'd say I R1 plus I R2. So that just essentially means that, hey, V initial minus I R1 minus I R2 has to equal 0. You sum it all up, it has to equal 0. That way you're not going to get like kind of infinite energy going through the loop each single time. And this applies even if your loop, the loop that you decide, so let's say this is my loop, right? I can decide, hey, I want this to be my loop, right? Now you got to be careful, right? If you say that's your loop, then as you're going through the battery, right, you're going to actually you're kind of going backwards, essentially, right? So you're starting at 0. When you go up the resistor, you're actually going to gain energy. You're going backwards, right? And the best way to really conceptualize it is just using these stairs, right? You're going up in potential. You're going up in potential. And then as you go through the battery, you're going down in potential. The voltage law would still hold, regardless of what loop you do. You could have, I don't know, a wire like this. voltage law still holds. You could say this is loop 1, right? And this is loop 2. Wait, would this even work? Wait a second. Because then you can also make this your loop, right? But then, oh, that's interesting. I don't think any current would even flow through this wire, right? Because if this was the loop I chose right here, you're going to be maybe gaining energy and then gaining energy, or if you go the other way, losing energy and losing energy. So I don't even know if any current would flow through here. But regardless, if you had stuff like a parallel combination thing going on, I'm really bad at drawing resistors. You could use loop rule here, right? And here, and then the whole thing. And it's just about deciding, are you going with the direction of current, or are you going against the direction of current? So for a resistor, if you're going against the direction of current, you're going to be gaining energy, because typically current would be losing energy if you're going the opposite way. So that's how you decide, hey, should this IR be positive or negative? Are you going with the current? Yeah, then it's going to be negative, right? Because you're for sure losing energy if you're going through the resistor. But if you're going against the direction of current, yeah, it has to be positive. So that was just a quick little thing on voltage, I guess. The voltage law, loop rule also is called. And yeah, hopefully this stuff makes sense. Bye.